In this video, we'll be talking about the different types of bonding that can occur between atoms, as well as the factors that determine what type of a bond will form between atoms of different elements. By the end of this video, you should be able to explain how ionic bonding works, explain how covalent bonding works and the different types of covalent bonds, explain how metallic bonding works, explain how all of this is related to electronegativity and Coulomb's law, and predict the kind of bond that will form between two elements based on their position in the periodic table. Before we get started, I want to explain something about the models we'll be using. Remember that we use models in chemistry to represent concepts to make them easier to understand. For the next couple sections, we'll be using the Bohr model, or the shell model of the atom. You know, the one that looks like a solar system with the different energy levels. Even though it's not the most accurate representation of what atoms really look like, it works very well for thinking about these concepts. Let's start talking about electronegativity, since this has a lot to do with what kinds of bonds will form between two particular atoms. Electronegativity is an atom's tendency to attract electrons to itself in a chemical bond. And just like many of the other periodic trends we talked about, atomic radius, ionization energy, and electron affinity, electronegativity has a lot to do with things like effective nuclear charge and the distance the valence electrons are from the nucleus and Coulomb's law. And we see some patterns with electronegativity that are similar to some of the other periodic trends. The tendency to attract electrons, electronegativity, increases as you move to the right in the periodic table. This makes sense because as you move to the right, the effective nuclear charge is getting larger. Electrons are getting pulled closer to the nucleus, and you have atoms that are getting closer and closer to having filled valence shells. Electronegativity decreases as you go down a column. Think about it. The valence electrons are getting farther and farther from the nucleus as we add more and more energy levels or shells. As the distance increases, the force of attraction on the valence electrons is less. These atoms become less and less interested in gaining electrons. Some of them are quite happy to lose electrons. Remember how ionization energy gets lower and it gets easier to pull off electrons as you go down the column? Similar things are happening here. Electronegativity is measured using the Pauling scale. There are no units to this, it's just a way to compare things. Fluorine is the most electronegative atom, and it's assigned a value of 4.0 on the Pauling scale, or depending on the periodic table, something very, very close to that. Cesium and francium are the least electronegative, and they're assigned values of only 0.7. Another way to draw our arrow would be like this. Electronegativity generally increases as you move from the lower left of the periodic table to the upper right. You'll notice that helium, neon, and argon aren't assigned electronegativity values. They don't want to take on electrons. They like the way they are. Electronegativity determines what type of bond two atoms will form together. It determines whether a bond will be ionic, nonpolar covalent, or polar covalent. One way you can predict what kind of a bond will form between atoms of two different elements is to compare the electronegativities of the elements you're looking at. You calculate the difference between the electronegativities of these two atoms. Only the absolute value is important here. Now, different textbooks do this a little differently, but the numbers in these tables are more or less a general rule of thumb. The electronegativity difference is the smallest for nonpolar covalent bonds, which we'll talk about in a minute. It is the largest for ionic bonds. Let's talk about ionic bonds first. In ionic bonds, there is complete transfer of electrons between the two atoms forming the bond. You have an atom that's really electronegative and wants to hog electrons, and another atom that is very happy to give up an electron or two. The more electronegative element snatches an electron, or a couple of electrons, from the other atom, and it becomes an anion, which is a negative ion. The less electronegative one happily gives up its electron to become a cation, a positive ion. The ions, now oppositely charged, become attracted to each other through electrostatic forces. The strength of the ionic attraction is determined by Coulomb's law. The larger the charges are, and the closer they are together, the larger the electrostatic or Coulombic force is, and the stronger the bond. Ionic bonds tend to happen when the electronegativity differences are greater than about 1.8. And this tends to happen when one of the atoms is a metal and the other is a nonmetal. Let's take a peek at sodium chloride. Chlorine is an electron hog with an electronegativity value of 3.15. Sodium has an electronegativity value of 0.93 and is very happy to let chlorine have its electron. The electronegativity difference is 3.15 minus 0.93 equals 2.22. That's greater than 1.8, so our bond is ionic. You see the same phenomenon with potassium bromide. Potassium has an electronegativity value of 0.82, but bromine's is 2.96. 2.96 minus 0.82 is 2.14. That's greater than 1.8, so this is an ionic bond. When atoms form ionic bonds, the total number of charges on the cations must be equal to the total number of negative charges on the anions. But spoiler alert, even though in formulas we usually think about one ion and another ion, that's not really reflective of what the actual physical arrangement of ionic compounds is. Ions generally don't hang out in pairs or small groups. They like to form three-dimensional lattice structures when they're solids. We'll be talking more about this in the future. Now let's talk about covalent bonds. Covalent bonds are formed between two nonmetals. They're formed by atoms that don't really like to give up their electrons completely. They like to share electrons, and they like to do this in a way that lets them fill their valence shells. For most of these elements we'll be dealing with, these atoms like to have a full octet. That means they want the s and p subshells in the outermost shell or energy level to be filled. Sometimes it takes one atom to do this. Sometimes it takes two or more atoms to do this. It all depends on what's needed to form a stable octet, like this carbon has, or a stable duet in the case of hydrogen. There are two kinds of covalent bonds we like to talk about, nonpolar and polar covalent bonds, and which bond is formed depends on electronegativity. In nonpolar covalent bonds, there is equal sharing between the two atoms. This typically happens when the two atoms are from the same element. Here's an example of a nonpolar covalent bond between two oxygen atoms. If you look at the differences in electronegativities between these atoms, you get 0, and this is not too surprising because they're the same element. Sometimes nonpolar molecules can involve atoms of different elements. That's what you see in this nonpolar covalent bond between carbon and hydrogen. Although there's a little bit of a difference in electronegativity between the two atoms, it's only about 0.35. Nonpolar covalent bonds tend to form when the electronegativity difference is less than about 0.4, and 0.35 is. The other type of covalent bond is a polar covalent bond. Polar covalent bonds, like nonpolar covalent bonds, happen between two nonmetals. But instead of forming between two atoms that have similar electronegativities, they form between atoms that have different electronegativities, where one atom in the bond is more of an electron hog than the other atom is. The more electronegative atom pulls the electrons that are in the bond closer to itself, but the less electronegative atom doesn't completely give up its electron. The electron is shared, but it's shared unequally. The molecule develops two poles, one pole that's a little more positive and one that's a little more negative. The side of the molecule with the electronegative element gets a partial negative charge. We often denote this by using a lowercase delta with a negative sign. The side of the molecule with the less electronegative element gets a partial positive charge. We often denote this with a lowercase delta and a positive sign. This water molecule is a great example. You can see in this picture how oxygen is the more electronegative atom. It pulls the electrons in the bond closer to itself. This side of the molecule gets a partial negative charge. Now the hydrogen atoms, they don't give up their electrons, they still have them, but the electrons are farther away. The hydrogen atoms get partial positive charges. If you look at the electronegativity differences between oxygen and hydrogen, you get 1.24. This is consistent with the electronegativity difference you would expect for a polar covalent bond. The separation of positive and negative partial charges in a covalent bond is called a dipole. Sometimes you see this symbol, with something that looks like a plus at the more electropositive end of the arrow. The bigger the charge difference, the stronger the dipole. Now here's an important point. All polar bonds tend to have some ionic character. The difference between ionic and covalent bonding is not distinct, rather, it's a continuum. Compounds with polar covalent bonds have some very interesting properties that we'll learn about later. So, just to review, what type of bond forms depends on what the electronegativity difference is between the two atoms. But it doesn't just depend on this. It also depends on whether the bond was formed between a metal and a nonmetal, or whether it was formed between two nonmetals. Okay, let's move on to one more type of bond that's a little different from the others. This is the metallic bond. These bonds form between metals, especially the transition metals, which have a lot of unpaired electrons in their d orbitals, and these electrons can move around. Metallic bonding is not covalent and it's not ionic. It's really its own thing. Metals like to share electrons. I mean, really share them. The electrons aren't really attached to any one particular atom. They're kind of detached. It's as if you have a bunch of positive ions surrounded by a sea of electrons. We call these electrons delocalized. I say as if because metals aren't really made of positive ions. They're neutral. Even though a given electron may not be attached to a particular atom, it's still in the structure. These things are balanced, these things are neutral. The metallic bonding structure gives these metals some very interesting properties. Conductivity is one of these. Metals are very good at conducting electricity. And remember, these delocalized electrons, they can move all around. Metals are usually solid at room temperature, and they have low volatility. That means they're very hard to make into a gas, at least on this planet. Metals are malleable, which means you can deform them under pressure. They can be pounded and hammered into thin metal sheets. Another property is ductility, the ability for a metal to be drawn or pulled or stretched without breaking. We take advantage of this property when we make copper wires to conduct electricity. So, those are the types of bonding. You should now be able to explain how ionic bonding works, explain how covalent bonding works and the two different types of covalent bonds, explain how metallic bonding works, and explain how all of this is related to electronegativity and Coulomb's law. You should be able to predict what types of bond will form on the basis of electronegativity difference and where the elements are in the periodic table.